Hello everyone, my name is Nathan Herdig and I'm presenting my joint work alongside Drs. Joe Hollingsworth and Olga Scrivener called Visualization of Student Solutions as a Sequential Network. Our work is motivated by the presence of formative online education tools where students will submit an answer to a server, the server instantly decides whether the submission is right or wrong, and the students retry until they reach a correct answer.
Hello everyone, my name is Nathan Herdig and I'm presenting my joint work alongside Drs. Joe Hollingsworth and Olga Scrivener called Visualization of Student Solutions as a Sequential Network.
Our goals were to design a system that presents a classroom's learning traces in an intuitive visual format. As the project went on, we designed a metric to organize the visualization system, and then we developed tools to manipulate the data to assist instructors in understanding the visualization system and to identify intervention opportunities. Our system combines the learning traces of students across a classroom into a directed graph. We can transform the history of the answers that the students tried, like on the table on the left, into a graph like on the right. Each vertex on the graph represents an answer that a student tried, and an edge going from one vertex to another means that at least one student tried the one answer after the other. So here's a demo of our tool on some classroom data collected from 99 students. This is a web-based tool powered by D3, so users can click and drag like this to manipulate the graph. We used size as a visual heuristic. The more students try an answer, the larger its vertex is in the graph. Likewise, thicker edges means that more students took the same path. Our system is organized horizontally by what we call the distance metric of incorrect answers. It's calculated as the average of how many more answers students had to try before reaching a correct answer. It's a predictor of how close an incorrect answer is to a correct one based on the previous student's data. The correct answers are in green at the far right end of the graph, and the remaining incorrect answers are organized by the distance metric. Answers with a higher distance are placed on the far left, and answers with low distance are placed on the right, which are closer to the correct answers. The system offers a couple of features to help instructors investigate the data. First, we can select individual students' paths using the checkboxes on the left. This dims out the other data, so then the selected data will stand out. This allows instructors to view pieces of data in the larger context of the classroom. We can also select groups of students that all input the same answer with this button right here, which can help identify how one answer is related to another. For two answers that are similar, users can drag and drop one vertex on top of the other to combine their edges and recalculate their distance metric, so it simplifies the graph. For larger data sets where the graph is too convoluted to make much sense of, the zoom buttons in the top right can hide vertices that only a few students visited, so the more important pieces of the graph stand out. We conducted a usability experiment on 54 professors at our home university. We gave the participants a short introduction of how the tool worked, and then asked them to complete 5 multiple-choice questions. At each question, we asked them to use the graph's features to identify something about the data. In some questions, we gave the participants a screenshot, and in others, we linked to a web page with the graph. After the 5 multiple-choice questions, we asked some free response questions, asking for ways instructors might use the tool, as well as some opportunities for improving the tool. Our results from the multiple-choice questions were very promising, with 91.5% of the responses being correct. Each multiple-choice question included an I don't know or I'm not sure option, which constituted 5.5% of the responses. So only 3% of the responses were on truly incorrect answers that represented some misinterpretation of the tool. For the free response questions, the most common concern about the tool was its ability to retain its usability on larger and complex data sets that might have more cluttered graphs. This survey was conducted before the merging and zooming features from before were added to the tool, and we believe that the new features can help the tool scale more effectively. One faculty member, the second quote on this slide, noted that the tool could be used to tell whether students were using formal thought processes to answer a question or if they were simply guessing and abusing the online autograder to eventually find the answer through brute force. This can be done using the relative sizes of each of the vertices in the graph. Sparse graphs with many small vertices, like the one on the left here, mean that students didn't share many answers in common, which can be a sign of guessing. Meanwhile, a dense graph, like the one on the right, with only a few large vertices, means that the students likely shared similar lines of thinking when approaching the problem. Another participant suggested using the tool's data processing in real time to assist during active learning activities. This is something that we are interested in, and it's a goal in our future work. Building off the quote from last slide, we'd like to create what we call an early warning system for active learning activities. In the graph below, the vertices on the left side have a high distance from the correct answers, and so we'd predict that if a student just input one of those high distance answers, they'd take more attempts than normal to find the solution. On some student trying one of those high distance answers, we could alert a TA or an instructor that the student could benefit from some guidance to get them back on track. We'd like to perform a future study of the tool's efficacy by giving the tool out to instructors to use on their own data and investigate how the tool informs their classroom interventions. We'd also like to automate some of this analysis, such as whether students are guessing or using formal thinking, using measures from graph theory like connectedness and density. We extend our gratitude out to the faculty members who generously volunteered to participate in our usability study. We'd also like to thank the faculty members, graduate students, and undergrad students from Rose-Hulman, Clemson, and Ohio State University that have contributed to the project. Finally, we want to thank the National Science Foundation for their continued support. And that's the end of our presentation. Thank you for listening, and video calls permitting, I should be able to answer any questions that you have.